Hello, this is part 3 of Mini Robot Dog, which is a small quadrupedal robot using accessible, affordable parts like radio control servos and various other things. So this robot has compliant joints with a spring and a finger mechanism and 2 magnets and a Hall effect sensor, and that means we can sense how much force is being applied to those joints, and we can hopefully make those joints compliant, which gives us a much easier route to stability than a rigid robot. So this robot project is going to be open source. I'm going to publish all the CAD and code when I've actually made it work. So if you want to support the channel on Patreon or through YouTube channel membership, then check out the links in the description. And also have a merchandise store where you can buy t-shirts, bags, socks and various other things with pictures of things I've built over the years. This robot weighs about 5.9 kilograms, so it's pretty manageable. I can pick it up with one hand and so on. However, it could be lighter. As well as 3D printing, of course, we've got lots of metal in this. There's quite a lot of steel, in fact. So every one of these joints has some nuts, it has some 8mm studding, and it has 4 of these bearings, which are skateboard wheel-sized bearings with an 8mm internal diameter. And there's 2 of those in the joint and 2 in the separate compliant mechanism where the gear is. So that actually adds up to quite a bit, as well as the 8mm studding that everything's mounted on. So there's about 1.1 kilograms of steel in this build out of the 5.9 kilograms of the total. So we could have another revision perhaps, which would be based on aluminium tube and build clamps into the plastic parts to grip it, and then a plastic clamp and a stopper on the ends with a small nut and bolt in or even a zip tie doing it up to hold the legs on, so we could save quite a lot of mass there. For now I've got Metal Gear servos which are 20 kilogram torque, and of course there's 12 of them, 3 in each leg and 4 legs. So for now we're just going to see how it goes with that extra steel in before we make another revision. I think it's going to be okay, but we'll see how long it is before the servos fail. The main thing I'm going to do in this video is add all the Hall effect sensors so we can make those joints compliant and we can measure the force like we did with the first test leg we did in part 1, and also add an inertial measurement unit to the electronics so we can measure the tip of the robot and vary compliancy based on which way it's tipping to keep it stable. That is rudimentary compliance though, and rudimentary stability. What we will eventually do is actually have it take steps in the direction it's falling so it catches itself like a 2-wheel balancing robot. But first of all, a quick ad for the component sponsor for this video, which is Cool Components. They've provided the teensy, the circuit boards and various other components in this build. They're an Arduino, Raspberry Pi, Microbit, Adafruit, SparkFun and a reseller for various other people as well, and they have various components and sensors on their website. So check out coolcomponents.co.uk for loads of cool stuff. Right, the first thing to do is get our teensy out with its box and go and wire all the analog wires into these connectors. So there's my Teensy 3.6 in its little box, and all the white wires I wired in last time are the servo PWMs that come out to these connectors for each end of the robot. So I now need to wire in the analog wires as well and connect those up to the connectors for the Hall effect sensors. Then I'm going to add another piece of proto board to the top with a connector where we can mount the inertial measurement unit and a radio chip. So all the blue wires here are the analog ins which go to each end of the robot, 6 to each one, and I've also got this connector here for I2C, which is a bit nasty, and that's going to go up to the top board. Right, there it is with the MPU 6050 and the little connector sat on top and all the wires going to the teensy inside. I've put the electronics back in and wired in the Hall effect sensors to those connectors. I've also wired in ground and 3.3 volts because the teensy is a 3.3 volt device, so we shouldn't exceed 3.3 volts on its analog ins. So we're going to run those Hall effect sensors off 3.3 volts as well. The Hall effects are mounted in each leg and mounted here and here, and there's also one on the middle as well for those 3 axis. And these only draw about 8 milliamps each, so using the 3.3 volt regulator on the teensy, which is capable of 250 milliamps, is just fine. So now each leg is compliant, just like it was in the test video that I did in part 1. And I've tensioned these springs up quite a bit so it doesn't collapse under its own weight. But we've got all of those joints, each one is compliant. And all we're doing is taking that Hall effect sensor value from the 2 magnets, which get closer and further apart as we bend those springs, and we're adding that to the servo position each time the loop goes round of code, which is 100 times a second. And of course we can multiply that value up to make the effect greater, and we've also got that filter which is doing the filtering to slow down the deceleration when it returns to its point, and it returns to wherever I push it. So now we've got that on all of the joints and those are all compliant. So let's put that on its legs and see what happens. So the result of that now is that actually the whole dog is compliant, and of course if we put load onto all of those joints at once, they all spring down and pop back to their default position under control of that filter. All of the joints do the same thing, so I can push it this way And basically what we've got is the physical springs taking the initial load, and then we're reading the Hall effect sensors 100 times a second and having those servos follow that position. So we've basically got a hybrid physical and virtual spring, and we can push this right down. I've had to spend some time tensioning the springs up so they don't just collapse under their own weight, but we can push this around quite nicely onto each side, and all of those servos react using all three of those joints. I've now integrated that inertial measurement unit from the MPU 6050, so we've got that data for the roll axis, and I've only used the roll so far, and the effect of that is that we've got no compliance here. You'll notice it's turned off at the moment if I try and move this leg, but if I tip it sideways, the more I tip it, the more compliant those joints become on that side. And you'll find on this side there's no compliance, only what we've got in the spring, until I go and tip it back again the other way, and then the compliance starts working on those joints. And we're going to use that for rudimentary stability. So the plan is to take diagonal legs off the ground at a time and balance on two legs while the other legs are off the ground. So the problem I've got though is that on this axis I can't get a spring, or at least I don't have a spring strong enough to put in here, because otherwise, standing on the two legs, what we find is that actually the robot skews quite badly. So for now I've just zip tied that up, and we're not going to worry about the compliance on that joint. Most of it's taken by the knee and the hip in any case. And off it goes. So you can still see there's some twist in there, but I think the mechanics are sound enough that we can make this walk. Now this isn't a very good system of stability. You can see it's not totally perfect, but I'll talk a bit more about that in a moment. But I'm pretty happy with what we've got so far. I'm happy enough with that, but what does it look like with compliance turned off, you might ask, and the stability turned off? Well, actually, in some of those shots it was turned off, so it doesn't make that much difference, although I know it's there. And the reason for that is that the dog is quite light, and of course we've got that natural spring in those mechanisms I've built anyway, so if it slightly tips and one leg goes into the ground, instead of being a really rigid leg that pushes the whole dog back and pushes it all over the place, which is the problem we had with openDog, in fact it just complies with the ground a little bit anyway, and it kind of sorts itself out. So that's really good basis to continue. I'm pretty confident we can make this walk now. So let's talk a little bit about that. So I mentioned that what I've got here isn't a very good system of stability, essentially making one side of the robot softer, and I'm not even doing it back to front, and it is actually quite long. So that'll make it even better. But what we really need to do is make it operate like a two-wheel balancing robot. So you may remember I've built a couple of those, the LG robot and Sonic the Hedgehog. And essentially what that does is drives faster to catch itself as it's falling in either direction based on a PID controller. So the wheels are going faster, they accelerate towards the target, and they try and get the mass back underneath the robot. So what I think we need to do to walk in a straight line, at least with a robot like this, is essentially control the speed that the legs work in that walking motion, so that they basically go faster if it tips forward and slower if it tips backwards, so that basically we can compensate and try and keep the mass on top. But in order to make that work, we're going to need a kinematic model. So a kinematic model is basically a mathematical model with all of the joint angles and limb lengths, which would allow us to calculate with trigonometry and Pythagoras the position of the foot based on all of the joint angles. But what we actually need to do is do that the other way around, so we need an inverse kinematic model. That means we can place the foot wherever we want in X, Y and Z coordinates, in straight lines, in Cartesian coordinates, and it will work back all the maths and work out the joint angles and where to position the servos. And that means that I can move this foot in a straight line backwards and forwards, for instance, so that we can move the dog's body in a perfectly straight line backwards and forwards, and the maths will take care of solving all those joint angles as we step through all of those positions, as we interpolate through those positions from point A to point B, and that will do that for all three axes for all of the legs. Now I did this before for openDog, and we're going to do that again for this robot, which is significantly easier. And the reason it's easier for this robot is we only really need to work it back to the joint angle, which we can easily work out what the angle is from the servo, because the servos are rotary and they're directly driving the joints. With openDog we had ball screws with levers and another triangle we had to work out, so there's a bit of extra maths. So next time we're going to add in a radio receiver and we're going to use a remote, probably the openDog stroke Sonic remote that has two 3-axis joysticks, so we can solve our 6-axis kinematic model, although we really only need 4-axis for this. The 3 translation axis and 1 of yaw. We don't really need the pitch and roll, but they're probably useful to solve if we get that far. So that's going to happen next time, and after that we can try and make it walk. Hopefully the legs move fast enough that it can actually catch itself as it tips, and that remains to be seen. If we can't make that work, then we'll have to walk with a minimum of 3 legs on the ground, which is pretty much statically stable and doesn't need any of the dynamic stuff. But we're going to try a dynamic model first with the trot gait using diagonal legs. So don't forget to subscribe for more on this project and all the other projects. I am going to publish this project as open source, so you can find the link to the CAD and the code so far on my GitHub, and the link is in the description to this video. If you'd like to fund me on Patreon or for a YouTube channel membership, then that really makes all the difference to the projects. And of course I have my merchandise store, and I'll probably have a t-shirt made of this soon. Thanks again to Cool Components for supplying the components for this build. That's all for now.